Okay, let's see what we covered in our last lecture. So in our last lecture, well, we finished talking about chapter 8, right? And first we talk about AEP, and then we talk about the properties, right? So I think I went a bit fast last time. So just read the book if you have some, you don't understand everything. I think I didn't go to the proofs. I think most of the proofs are pretty straightforward, except the entropy power inequality. So that's pretty hard. Yeah, and you want to go over that. I think in the book they provide the proof of entropy power inequality in chapter 11 or chapter 17, I think. So it's very late. But okay, so here is the definition of the typical set, right? So basically the definition is exactly the same as before, right? The only difference here is that now consider x is continuous, and so that's that's in the real domain, okay? And then all the properties are pretty much the same as before, right? So basically the typical set will occupy all the probability, right? And upper bound and lower bound. So both of them is more or less 2 power n times the differential entropy. And similarly, for here we need to, this holds for large n and this holds for all n, right? The reason is that we need this here, right? So the probability less than 1, so we have a 1 here, but the probability bigger than 1 minus epsilon. That's why we have this 1 minus epsilon, right? So same as before. Okay, and then we cover some properties. So for all these properties, they are exactly the same as before, right? So we don't need to spend too much time on that. And for those properties that are relatively new, first is the shift invariant. So basically, if we add a constant on the random variable, right, we don't change the differential entropy, right? And then if we do a scaling, so this is what we got, right, for the scalar case. But if we use a vector multiplied matrix, and then this is what we got, right? So here we need log of the determinant of the matrix here, okay? And then we focus on the Gaussian random vector, right? So if a vector follows a Gaussian distribution with mean mu and the covariance matrix K, right? And here is entropy, right? So we're going to use that a lot because, in wireless communication, the most popular channel model is it's a kind of Gaussian model, right? Where we assume the noise is Gaussian. That we're going to go over that today. Okay, and based on that, we can compute the mutual information. So if x and y are Gaussian distribution, and then we can compute to prove this Hadamard inequality, right? So this is if we can use the entropy to prove that, right? So if we do not use entropy, so basically what we do is that we use this property to prove that, right? So if we do not use that, if we do not use the entropy, to prove that, then how can I prove it? Any idea? Yeah, if you see this kind of form, probably we're going to use some, geometric mean, arithmetic mean to prove it. Okay, but entropy probably is easier. Okay, and then we have the maximum entropy inequality. So here, important thing is that, okay, so if I have the distribution that with the same covariance matrix, okay. So under condition that we have the same covariance matrix, then the Gaussian distribution will maximize the differential entropy. Okay, so this is different from the discrete case, right? Discrete case, so uniform distribution will maximize the entropy, right? But here, so if we, let it be any value, right, and fix the covariance matrix, and then the Gaussian distribution will maximize the entropy, okay? And this is very important. We're going to use that today. And then it's entropy power inequality. So basically we show, okay, if x and y are independent and the Gaussian, right, then they are equal because all of them will equal to the variance, right? But if x, y are not Gaussian but independent, then we have this inequality. We don't show it, right? We just show the intuition of it. So in the last lecture, but so this is a pretty important way we may want to remember it. Okay, and then so for the estimation problem, so if we have x hat, that's the estimator of x, and then the mean square error will be bigger than this quantity. Okay, so by the way, so if x hat is the estimator of x, right, and if you consider the mean square error estimation, then what is x hat? Right, what is the best estimate of x? Louder?
Maximum likelihood? Is that what you're talking about?
Oh, no, here we'll consider mean square error estimation, right? We want to minimize that.
The mean then.
Yeah, the mean, exactly, right? X hat will be equal to the expectation of X. Okay, that clear? And then if you consider this case, right? So if let's say we do not sample X, we observe Y, and then we estimate X from Y. So X hat is a deterministic function of Y. Okay, and then in this case, so the mean square error will be upper bounded by this. Okay, so by the way, what is the minimum mean square estimator? In this case,
It's a conditional expectation.
exactly, expectation of X given Y, right? So that's basically very good, very good. Okay, yeah, and you better know that. Okay, so we will not use those a lot, but this one is pretty important. Then we'll probably use that a lot. Okay. All right. Yeah, let's see what we're going to cover today. So we only have 6 lectures left, right? So we will, I think we're gonna spend 2 more lectures, or a little bit more than 2 lectures on chapter 9. And then we're going to cover the rate distortion theory in the end. Okay, so that's the agenda 34. Yes. And today we're going to, where's my pen? Cover chapter 9. So basically, chapter 9 is about channel capacity. So it's very similar to what we covered before in chapter 7. Okay, the only difference here is that now we're considering a continuous random variable, and in particular, we consider a very specific channel. Okay, so before we consider DMC channel, right? Discrete memoryless channel, right? But here, what we consider is AWGN, additive white Gaussian noise channel. Okay. First, we need to introduce what is the additive noise. Okay, and then we'll talk about the channel capacity of additive white Gaussian noise or AWGN channel. So who know what an AWGN channel is? Okay, so yeah, now we use, yeah, except you, right? So you didn't take this communication component or system, whatever class. Okay, it's fine. So I'm going to cover that anyway. And lastly, so probably we don't have time to cover that today, but we'll cover that next lecture. So the last part is the capacity of other channel. Okay, obviously, we're going to derive the capacity of other channel from the capacity of AWGN channel. Okay, so we're going to cover some specific kind of channel that's very relevant today. Okay, so this chapter is probably one of the most relevant chapter in the past, like maybe 30 years. Yeah, because of this, so we have so much development of wireless communication, 5G, 6G, Wi-Fi, and so on. Okay. So yeah, this can be, actually, this is not just theoretical, so we can use that to do lots of optimization in practice. Okay. Okay, so additive channel, additive noise. Okay, so basically the channel that we're considering is as follows, right? So before, for this case, we consider, the channel is a probability distribution, right? Here, the same thing, but we can have a more, visual representation of it, right? So here, in particular, so we'll assume the input is X, right? So that's a random variable. And then what the channel does is very simple. It just add a noise on it, right? And noise is the Z. And then we have Y, right? So remember here, so X, the alphabet of X and the alphabet Y, so they are the real domain. Okay, so we consider discrete time. Okay, meaning that so on the x horizontal, on the x axis, so we only have like 0, 1, 2, 3, and so on, right? But for the y axis, for the value of the random variable, so it can be anything in the real domain. It can be negative, and can be positive, can be infinity, can be whatever. Okay, so it's continuous alphabet, okay, channel. Therefore, so we're still considering digital communication, right? It's nothing to do with the analog communication. Okay, so we're still, but later on we're going to see that, we can use the Nyquist sampling theorem to convert it somehow. All right, okay. And for the noise z, so we assume that is continuous random variable. Okay, and here obviously y equal to x plus z, and this plus is just a plus, right? It's not the modulo operation that we discussed before. Okay, and this channel is called the channel with additive noise. Okay, so this is a channel with additive noise, right? Because noise is add on x, right? So in practice, so it is possible that the noise can be multiplied on x. Okay, but here we'll consider the most simple case. All right, and in this case, so we can compute, some quantities here, right? For example, let's compute what is the differential entropy of y given x, right here. So both x and y and z, they are continuous random variable, right? So let's see what that equals to. Okay, h y given x. Okay, so that equals to what? Y equals to x plus z, right? And given x here. Okay, so what is that? What is this term? Say again?
HC, right?
Yeah, why?
Because you're given x and z are independent.
Oh yeah, you're like, yeah, there are two steps, right? The first step is that, okay, so, but you're right. We know x, right? Knowing x meaning x is constant because we know that, right? And then, so a immediate step is that this equals to this, right? And what property do we use?
Shift invariance.
Exactly, shift invariance. Right, and then this equals to hz because we assume xz are independent. Yeah, because the noise normally is given by nature, right? So it's independent on our transmit signal. Okay, great. So now we use the shift invariant property, okay? And normally, so x is our transmitted signal in practice, right? So since it's a real signal, and then, so we need the important constraint on x, so which is a power constraint, right? Because we can now transmit with arbitrary large power, okay? So we have a power constraint here. And for the mathematical, convenience, so normally for this power constraint, so ideally we're going to have a instantaneous power constraint, right? For example, let's say p should, the power of x should be less than a p, right? But here, for mathematical convenience, so we assume that the power of x, the expectation of x squared, so that's less than p, right? So consider the expected value of x squared is less than p. Okay, so that is what we do here. Okay, one simple example is that x could be plus minus square root of p, right? If we take x only like two values, and then that'll be it, right? So we use that in practice. Do you remember what does that call? What is that called? So if we take x be only two values, let's say plus square root of p minus square root of p, and then what is that modulation called?
Just like binary phase shifting.
Exactly, but normally we call it exactly, that's BPSK, right? Binary phase BP shift keying, right? Heard of it? No, it's fine. It just means that. Okay. Okay, great. So yeah, this is the basic system setup, and as we discussed in chapter 7, so normally in practice, right? So X is a channel code. Okay, so we map our message M to X, right? But we do not only use one X. We use a code word, so which is a number of X, right? So basically, in practice, so basically, this is what we got. Okay, we transmit a vector, and that vector represents a message. Okay, so that's channel coding. Okay, so now if you consider a vector, right, X, it's upon design. It can be anything we want, right? But Z is given by nature, right? So here, one very important assumption for Z is that Z are IID. Okay, so we assume Zn equals to Z1, Z2, up to Zn, right? So we denote that as Zi, I from 1 to n. Okay, so we assume that they are IID. So if Zn is an IID sequence, okay, then we say Zn is white. Okay. Otherwise, we call it colored noise. Okay. So basically, if Z are IID distributed, then it is white. Okay, so yeah, so that's basically everything I want to cover for this topic. Okay. So what does this white mean?
The spectrum has equal parts of every.
Yeah, exactly. So basically, the technical meaning of white is that the power spectrum density of Z has to be a constant everywhere, from negative infinity to plus infinity. So that's the meaning of white, right? So it's like the white light, right? It has all the frequency, all the colors, right? So if Z is white, it basically means that in the frequency domain, it is equal everywhere. Because it's a random variable, right? So we do not compute the Fourier transform of Z. So what we do is that we compute the power spectral density of Z, right? So what's the power spectral density in the time domain?
The autocorrelation.
Exactly, autocorrelation function. Okay, yeah, those are kind of complicated. So if you want to know more detail on that, you can take a look at my lecture notes, lecture video online. So I have my other course. So I talk about how we derive those kind of things in very, very detail. Okay, so it's not that trivial. So we need a few lectures to compute everything there. Okay, and next we'll talk about the capacity of AWGN channel. So here, what we cover is that Z is white, right? So we know what's the meaning that Z is white. So now we need to cover the other part, right? Z is additive. We know additive, and we know white. And what we do not cover is it's Gaussian, right? So we assume Z is a Gaussian distribution. It follows, for example, this distribution with mean 0 and variance n. Okay, so this is the expectation of Z, and this is basically the variance of Z. Okay. All right, and then in this case, so Yn equals to Xn plus Zn. So this is called AWGN channel. Okay, so basically Z is IID and Gaussian distributed, and then it's called AWGN. Okay, very good. Any questions? Okay, if not, so now let's try to compute the capacity, right? So probably, because we learned chapter 7. Okay, so now there's some difference here, right? But probably you can already guess, right? So let's consider those. So we start, just from, our intuition, right? So probably you may guess the capacity of this channel would be what? Mutual information, right? So it should be the maximization of this mutual information, x between y. Of course, we're going to show that mathematically, right? But here, you'll see, right? So all the property for the mutual information, for the entropy will hold for differential entropy and mutual information, right? Probably repeat more or less the same procedure, you're going to get it, okay? So here, the maximization is over all the PDF. Right before, it's over all the PMF of x. Here, it's over all the PDF of x. But we'll have one more constraint, right? So this is the difference. So we need to make sure that x squared, the expectation of x squared, is less than or equal to p. Okay, so this is our maximization problem. Okay, let's see how we can maximize it, right? So the idea is pretty much the same as before. So yeah, before we introduce a universal approach to do the maximization using the KKT condition, right? But we consider the binary erasure channel, consider the binary symmetric channel, right? So probably what we do is that we expand this mutual information and take a guess, see what kind of input distribution will maximize this y, right? For example, if it is a discrete distribution, then the uniform distribution will probably maximize this guy, and then we compute that, right? So here we'll do pretty much the same thing, right? The only difference here is that in order to maximize this guy, we need to take not uniform anymore. We need to take the Gaussian distribution, right? Because here, so this constraint basically tells you that the variance of x has to be upper bounded, right? So in order to have a higher capacity, probably you're going to take this equal to p. Okay, so it means that with the same variance, then the Gaussian will maximize the entropy. So we're going to use that. Okay, it's the logic clear? Okay, great. So basically, yeah, this is what we're going to do. And the next step is that so we can simplify the second term, right? So here, y will be nothing but x plus z, right? And then the second term is hz, right? As what we have seen before, and we know what hz is, right? Yeah, because z is Gaussian distribution already, right? So that equals to what? Half log 2 pi e times the variance n, right? So basically that's the. Okay, so now the tricky part is the first one, right? So for this guy, as we said before, okay, so now we know z is Gaussian, okay, and the Gaussian distribution will be maximize this entropy, right? How to make x plus z Gaussian? Right, we know z is Gaussian already, right? And we want x plus z to be Gaussian.
So x has to be Gaussian.
Exactly, x will be a Gaussian distribution, right? So now what we do is that we let x follow a Gaussian distribution with 0 mean and p. Okay, and then basically it will be x plus z will be a Gaussian distribution with a mean 0 and the variance p plus n, right? Then we can write down the entropy as this: 2 pi e, and then p plus n, and then we add this term, 2 pi e n. Okay, and then what we do is that, so now we have a log here, right? We can combine those two. Oh, sorry, there's a minus sign, not plus. Okay, and then what we got is that, so if we combine this and that, so we use this divided by this, right? This 2 pi e will be canceled. Then what we have is what? 1 plus p over n. Okay. Right, p plus n divided by n, so that will be 1 plus p over n. Okay, so this is basically the channel capacity, right? So now we get C prime equals to this. Okay, later on we're going to show that will give you the channel capacity. So here is from intuition, right? Okay, and one more thing we want to emphasize here is that, so what is this term, right? So this term on the top is the power of the signal, the power of the transmitted signal, right? And downstairs is the noise variance, right? The signal power divided by noise power, that's called, exactly, signal to noise ratio, right? That's called signal to noise ratio. All right. So any questions so far? Okay, so I think one thing I want to emphasize here is that if you work in communication, so you will see this formula a lot, right? People just use this formula to denote the channel capacity. So that basically tells you the best you can do for this channel, right? So two remarks. Number one, so let's say if the signal-to-noise ratio increases, then the channel capacity will increase. So which makes sense, right? If you have more signal-to-noise ratio, then you could transmit more. Okay, and the other remark is that, okay, so here, so this can be only achieved by what? A Gaussian distribution for x, right? If x is not Gaussian distribution, so this is not precise, right? In practice, x is not Gaussian, or at least, it's not Gaussian. Okay, so why x cannot be Gaussian? Yeah, because the range of Gaussian is from negative infinity to plus infinity, right? So we cannot have infinite power, right? So here the constraint is average power, right? But in practice, we always have to truncate it, so we cannot get a Gaussian. Okay, so there's some remarks. When you see this formula, you may think a little bit. So is that valid in the scenario that I'm considering? So in most of the papers that you have seen, probably it's not extremely valid, but we still use that because that gives you an indication of the best performance of your system. You cannot achieve it normally, but still.
Are you
Yes.
Are you saying we can't pulse shape our signal Gaussian because it's infinite? Is that what you're
Yes, we cannot get Gaussian exactly, but we can more or less get Gaussian approximately. Yeah, maybe I'll say one more word here, right? So basically, in practice, what you do in a communication system is that, you do some, channel coding, but normally the channel coding is not designed for Gaussian channel. It is designed for example, BSC, BEC. You code a bunch of 0 and 1, 2, 0 and 1. Okay, and then you have a bunch of channel code 0 and 1. And then you do a bunch of pulse shaping. You have a pulse for each 0 and 1 or whatever, right? And then you do some filtering and then transmit it. Okay, and combine all of this together, probably X will look like a Gaussian. Does that make sense? Right? But normally people do not talk about that. Okay. Okay, great. So now, let me write down all the definitions here. So which is pretty much the same as before. Okay, before we prove the channel coding theorem. So this is pretty much the same as before. It's a good recap of what you have learned before. Okay, let's see whether it makes sense or not. So definition, we define the codes with power constraint. Okay, we say a Rn code with power constraint P consists of the following. Okay, so number one, we need to define, what is the index. So that's capital M. So this is pretty much exactly the same as before. So we index from 1 to capital M, right? And this capital M is a cardinality of the M, right? And that equals to 2 power nr, right? Which means that R will equals to 1 over n log M. Okay, so that's the same as before. Second one is the code book. The code book definition, again, is very similar to before, but we need to give the power constraint here, right? So in the code book, we have x1 till x2 power nr, right? So that's all the code word. And for each xi, so we have xi1 to xin, okay? And then for all I, so we define this guy less than np, okay? So assume that the power basically is the average power will be less than or equal to P. Okay, so that's basically the code book. And next, we need to define what is the encoding function and what is the decoding function, right? So number 3, encoding function. Okay, so this is a function f. So that's from capital M to C. Okay, and we write xm equals to fm. Okay, and for the decoding function, so we use g normally, right? So that's from yn to m, right? We say m hat equals to g y. Okay, so the only difference here is that we have a power constraint, right? So now the average power probability of error so that is defined by this. Okay, and this guy is the error of message m given xn is transmitted, right? So this guy equals to the probability that gyn not equals to m given xn equals to xm. Okay, very good. So this is basically the definition of a channel code. Okay, so very similar as before. Okay, and then let's define the capacity. Oh, no, it's 26, right? Oh, we have lots of time. So we should, yeah, so we should do until 40, right? Okay, great. Capacity. So the definition of capacity here is exactly the same as before. Okay, so the only difference here is that we have a power constraint. Okay, so that's the only difference. Yeah, I'll still write it. So a rate R is set to be achievable for an AWGN channel with a power constraint P if there exists a sequence of a Rn code Cn satisfying the power constraint such that the maximum error probability will goes to 0 as n goes to infinity. Right, so that's the maximal error probability. Okay, so this so we have seen that before. Okay, then the channel capacity is defined as C equals to the supremum of R, where R is achievable. Okay, so you can see here the emphasis here is that we have a power constraint P here. Everything else will be pretty much the same as before. Okay, and given all the definitions, so now we're ready to present our theorem. Okay, so this is channels second coding theorem for EWGN channel. With power constraint. Okay, so now I can see, how much Shannon's paper covered, right? So far, everything we covered is in Shannon's original 1948 paper. Okay, and we still have something didn't cover yet for the whole semester. Okay, so the capacity here is given by this. So that's exactly what we have seen before. So here the log, we take a base 2, right? Then it will give the unit of bits. Okay, and so we need to be careful on the unit of it. It's bit per watt, right? It's not bit per second. It's not bit per hertz. So it's bit per channel use. So we use the channel this number of times, right? We use the channel one time, and this is the number of bits we can transmit. Right? For example, if we design a channel code in this way, the channel code in this way. So how many channel uses we have for one code? And exactly, right? So this is the number of bits per channel use. Okay, very good. And clearly that equals to the C prime that we have seen before. Okay. Okay, great. So now let's get started to prove. Let's denote that this is a theorem star. And then, so we're going to prove it. Proof of theorem star. Okay, the proof here is, again, very similar as before, right? So yeah, let's go over it very fast. So the first one, we're going to show the achievability. Okay, so what should we use for achievability? Random coding, right? Very good. So before we use random coding, so here we also use random coding. Oh, yeah, there's one important thing I didn't emphasize. So now we assume an EWGN channel, and the noise is IID, right? Therefore, our channel is what? Still a memberless channel, right? So we're not going somewhere crazy, right? So it's still very similar compared to before. So it's a memberless channel. Okay, so basically the idea is random coding. So in order to use random coding, so we're going to design a code book, right? Code book generation. So, right, so before, how did we generate the code book?
Before we used the PMF, so
Yeah, the key is all the code, all the elements in the code is IID generated, right? So here we do the same thing, okay? So we use the, random, we generate the code in an IID fashion, right? So basically here we have x1 up to x2 power nr, right? And for each element of each code word, we're going to generate it in the IID fashion, right? For example, here for xi, we have xi1 up to xin, right? So we're going to generate them in the IID fashion, okay? But, before, for the discrete case, what did we do is that we assume there's a PMF, px, and then we generate x corresponding to px, right? But here, so we can say, okay, we generate each x using fx, right? But we know what is good to do, right? So basically what we're going to do is that we're going to generate each of these x follow a, what? Gaussian distribution. That makes sense, right? So basically for each ij, so that will follow a IID Gaussian distribution with zero mean and the p minus epsilon for the power. Right? So does that make sense? So why we need a minus epsilon here? Yeah, we just take a bit smaller variance, right? Because we have this constraint here, right? So we want this to hold, okay, with high probability as n becomes large, right? Then if we have epsilon there, we can show that. Okay, very good. Okay, so this is a code book generation. Okay, so again, it's still the same as before. We can consider this as a 2 power nr multiply n. So this matrix and each row is a code word, right? The same as before. So now let's define what is the encoding. Okay, so encoding is nothing but xm is the m's row of the generated code book. Okay, so assume the code book is 2 power nr multiply n this matrix, right? So each row would be a code word. Okay, okay, great. Next is decoding. What should I do for decoding? Yeah, this should be straightforward, right? So why we want to introduce AEP here, right? So we use typicality decoding. Okay, so decoding is the joint typicality decoding, right? We claim m hat is our code word. It's our message that in n. So if this is the unique index such that x m hat and y, so they're in the typical set. Okay, jointly typical, right? So this is nothing different compared to before. Otherwise, we're going to declare error. Okay, otherwise. But here we need to be, be careful on one thing, right? So before the error event are two kind of error event, right? One kind of error event is that, so m and y, they're not typical. Okay, and the other error event is that there exists some other index that are typical with y, right? But here we still have those two events, right, going on, but we have one more error event. What is that? See, what's the only difference between this and the discrete case? So that's the what? Power, right? Right? So because our power constraint here is a hard constraint, okay? And x is a Gaussian distribution. So there will be some chance that, this will be bigger than this, right? So then we have another error event. Okay, so there we do need to include the case when the chosen code word does not satisfy the power constraint. Yeah, you know what I'm writing here. Okay. Any questions so far? Okay, great. The next step is to analyze the power. Is to analyze the error probability, right? So the first step is what? Analyze the average power error probability, right? And next step is to,
Expiration.
Exactly. That's the last step, right? The second step is that, okay, we say, okay, so now it's an expected error, right? And now we say, okay, there exists a code word that satisfies this. We get rid of the expectation and then use the expurgation, right? And then we don't go to the second and third step because that's exactly the same as before, right? The only thing we do here is to compute the expected average error probability. Okay, so that's what we do. Okay, so the probability of error is given by this, right, as we said before. So that's the probability that, okay, again, so we're going to use the technique we used to show the discrete time case, right? We'll only need to consider message 1, right? We do not need to consider other messages. Or just consider, so this equals the probability that this guy does not equal to 1, given 1 is sent. Okay, so yeah, this is what we showed before. Okay, so now we need to define what is the error event, right? So we let E be the conditional error event. Okay, now, then we decompose E, right? So E can be decomposed as, so we have one more event to consider, right? E0. So that's the power, the event that if our code word does not satisfy the power constraint, and then we have E1 complement, E2, E3, whatever, up to E2 and R, right? And here we say E0 is an event that this power constraint does not satisfied. Okay, so that's E0, and everything else will be the same, right? And yeah, we just say EI is X in I and Y in, so that is in the typical set of X and Y. Therefore, E1 complement is also included. Okay. Okay, and then it will be similar as before. So basically, we have our error probability. So we denote that as probability of error. Okay, so that's basically this term. Okay, so probability error is the probability of E0 union E1 complement union E2 union up to E power and R. And then we use the union bound again, right? So this would be less than or equal to E0 plus P E1 complement plus P E2 and so on. Okay, so now we can observe something here, right? So for example, for the first guy, so which is a probability that the power will be bigger than P, so that'll be let's say that'll be definitely less than epsilon for some large n. Why is that? Yeah, because it's the mean of the variance, right? So basically that'll converge to the variance. And then it's the mean of x squared. It converts to variance, right? So we can show it will be true that it will hold using law of large numbers. Okay, so because our probability is is P minus epsilon. Okay, again, second term will be less than epsilon because of AEP. Right? So, right, with high probability, there will be some, there will be the x1 will be jointly typical with y. Okay, because of AEP, we have this, and then for those, okay, the derivation will be exactly the same as before, right? So basically, this will be less than I from 1, I from 2, not 1, to 2 power nr. Okay, and then we take upper bound on each probability, right? So if for some other x that's jointly typical with y, the probability is what? So remember that 2 power n times mutual information minus 3 epsilon, right? So this is what we have shown before, okay? So we take upper bound for each of the error probability. Okay, and then for that, so this equals to 2 power nr minus 1 and 2 times 2 power this guy. Okay, and then we can show this will be less than or equal to this guy, the mutual information minus r minus 3 epsilon, right? Therefore, we can show that if r is less than this guy, and then we can show this guy will be less than epsilon. Okay, so this procedure is the exact same as before. The only difference here compared to before is that we have this additional term, but that can be taken care of by the law of large numbers. Okay, therefore the conclusion is that, so if r is less than, we need to make sure there's a minus 3 epsilon. Mutual information minus 3 epsilon, and then for large enough n, the error probability will be less than or equal to 3 epsilon. Okay, because we have 1 epsilon here, 1 epsilon here, and 1 epsilon here. Okay, and for the rest of step would be the same as before, right? So we use the expurgation and so on. Okay, so that's basically the proof for the achievability. Okay, so next class we're going to continue talking about the converse. Okay, great. Thank you.